Can I start? Okay.
Yep, we're good to start. Yep. In this breakout session, we'll have 3 presentations from the winning teams. And we're delighted to start with Thomas, who will be presenting mixture of Gaussian posteriors with an improved Bayesian learning rule. All right, take it away.
All right. First of all, thank you for organizing this great competition. It was really a pleasure participating and fighting for the spots. And yeah, so my name is Thomas, and this was a joint work with Yusong Shen from Technical University of Munich, and Gian-Maria Marconi, Peter Nickel, and MTS Khan from Riken in Tokyo, where I'm also currently located, and it's 3:30 a.m. So I apologize if I'm a bit tired. All right, so let's start. Okay, so the question is how to construct a good approximate posterior. And yeah, so there are several principles one can follow. And the first one is to consider a single network at a minimum. So there's a sketch for this. We call this approach A, where we have the loss function, and we use some kind of optimizer to find a local or global minimum. And then we consider some kind of structured approximation at that minimum. So that would, for example, the Laplace approximation would fall into this framework. And one could use either maybe a generalized Gauss-Newton or Hessian approximation as the structure to get some kind of local approximation of the loss. But
looks like your slides aren't advancing.
Oh, the slides are not advancing. Oh my God. Okay. So you're still seeing the very first slide? Or?
Now I see slide 2. I can see your cursor now too.
Okay. Then let me change the presentation mode. Okay. Is it slide 2 visible now, or?
Yep. How to construct a good approximate posterior. It just shows the title right now.
Great. Yep. Okay. So this is things are showing up now also.
Yes.
Okay, great. All right. So yeah, this is the slide corresponding to what I was saying earlier. So the most simple way is to look at a single mode and consider some kind of structured approximation at the single mode. For example, Laplace approximation, where the structure is, for example, GGN or based on the Hessian. And of course, this doesn't capture the global shape of the loss function, as we've also seen in the talk earlier. So to get a better approximation, one can also explore the region around this minimum, the local neighborhood, and consider some kind of averaging of networks around that minimum. For example, using a variational inference approach, which considers a more global approximation. And finally, an ideal method would also consider multiple modes, and this seems to be the common theme in also all of the winning submissions, to look at multiple minima. And ideally, we would like to have a structured approximation which explores around multiple minima, so combining A, B, and C. And this was somehow the principle we tried to follow for our submission, to combine these 3 points A, B, and C to get a good global approximation of this loss function. And so here's an overview of the talk. I will talk about the Bayesian learning rule and how that rule helps us to achieve these 3 points, A, B, and C. Then the Bayesian learning rule can be approximated to give something called the variational online Gauss-Newton optimizer, called Wogen. I will briefly go into that. Then there's an improved version of Wogen, which we this was already published, but we kind of developed it for deep learning more for this competition, which we call IVON. And finally, I will give a summary of our results. Okay, so the Bayesian learning rule, what is it? It's a natural gradient variational inference method, and the rule updates the natural parameters of an exponential family distribution in order to maximize the elbow. And it looks like this. So we have the natural parameters lambda, and we do a gradient step on the elbow in the expectation parameters. And by an appropriate choice of exponential family distribution, the rule can implement, for example, structured approximations and due to its VI nature, provide also exploration around the minimum. And the rule can also be extended to handle mixtures of exponential family distributions to also cover multiple minima. And to learn more about this rule, there's a recent work online by MTS Khan and Harvard Rue on this Bayesian learning rule. And yeah, here's an example of the optimizer Wogen, which is a modified version of RMS-prop or ADAM, which can be derived as an approximation of the Bayesian learning rule when using a diagonal Gaussian, and the exponential family consists of diagonal Gaussian distributions. And it matches the performance on ImageNet of these RMS-prop ADAM type methods, but it improves the uncertainty estimates. And in the figure, we can see in blue the ADAM optimizer, in red the Wogen optimizer, and on a simple 2D classification example. And at the beginning, the trajectories look quite similar because the methods are very similar, but eventually this Wogen method will converge to a better solution, which is maybe in a more flatter minimum and due to the variational nature. So I mentioned this Wogen method is very close to RMS-prop, and if we put them next to each other, we can see that they're indeed very, very similar. The differences are highlighted here on this slide in red. The main difference is that Wogen evaluates the parameter at which the loss is evaluated at a perturbed point, and crucially also the perturbation strength is learned. So it's not fixed noise that is added, but the noise that we add to the parameter at which we compute the gradient depends on this scaling vector S used in RMS-prop. And there are some smaller differences also, but roughly this is the main difference. And a big difficulty for implementing this Wogen method in practice are these, per example, squared gradient computations that one needs. So for RMS-prop, one sums up the gradients and squares them, but for Wogen, it turns out to be better to square the gradients and then sum them up. And this is not supported in older deep learning frameworks. In JAX, it's no problem to implement it, but in PyTorch, this can be a struggle to implement. So this is a deficiency maybe of this method. And this is fixed by an improved Bayesian learning rule, which has been recently published. And the improvement is as follows. So the Bayesian learning rule can be seen as a first order approximation of a gradient flow ODE on the statistical manifold. And one can also consider a second order approximation of this gradient flow, which was published in this paper here. So this is some kind of improved version of natural gradient descent, which is a second order approximation to the time continuous natural gradient descent. And for a Gaussian family with mean mu and precision S, I've shown the equations here. Maybe they're not too important to really understand, but one kind of adds, shown in red, one has to add a second order correction term to the Bayesian learning rule, which has certain advantages, which here for the Gaussian distribution ensure that the precision matrix stays positive definite. And this is useful in practice because then we don't have to square the gradients anymore to have something positive definite, but we can use also a Hessian estimator, which leads us to the improved variational online Newton method, which we used for this competition, which is derived from the improved Bayesian learning rule. So Wogen we derive from the Bayesian learning rule, and this I1 we derive from the improved Bayesian learning rule. And the difference is that we replace, it's highlighted in green, the difference, we replace the squared per example gradients. We replace them with a reparametrization trick estimator of the Hessian matrix, of the diagonal Hessian matrix. And this works because of the red correction term, which ensures that even if the Hessian is maybe not positive definite, or the reparametrization estimator is a bit noisy, it still ensures that this S vector stays positive. And this allows a very efficient implementation because we don't have to do these, per example, squared gradients anymore. And we also expect it to perform better because we use now the diagonal Hessian instead of a squared gradient approximation, which is more faithful to the to the exact thing that we would want for our Gaussian variational family. Yeah, it's easy to implement in a deep learning framework. It's about as difficult to implement as Adam. And when using a single Monte Carlo sample to sample the parameters, it has almost the same cost as the Adam optimizer. So there's basically no overhead of using Adam, but one gets something which is a little bit Bayesian. And there's this gamma parameter, which I did not talk about, but it's some kind of damping or stabilization parameter, which makes the method more stable for deep learning, which we found to be quite crucial in practice. And for our submission, what we essentially did, we ran the algorithm on the right, this I1 algorithm with the added momentum, which can be found in the paper reference at the bottom. So this is the RMS prop version, and there's also an Adam version which adds momentum. And this one we used, and we combined multiple independent runs of this I1 method to construct a mixture of Gaussian posterior. And this was basically our solution. And how did we decide to use this method? So for the development phase, we looked at the ResNet 20 on Cypher 10 and evaluated some baselines for a single minimum. First one we tried was just plain SGD, which got an agreement of 91% and 0.14 TV distance. Then we implemented the Wogen method, which gave an agreement of almost 92% and a TV distance of 0.1057. And finally, we also implemented this I1 method, which gave the best results for the single minimum. And then we also tried to evaluate a baseline which covered multiple minima, which was just a naive ensemble of SGD, which turned out to be very competitive. So it gave 94% agreement and even a better TV distance than this I1 optimizer. But finally, the best result was achieved by using a mixture of Gaussian posterior using this I1, which with fewer mixture components, 8 diagonal Gaussian components, gave agreement of 95% and TV distance of 0.074, which led us to use this kind of idea for the final phase of the competition, where we had to do some parameter tuning. So I'm not a graduate student anymore, so I'm a postdoc, but I also did some descent. And for the final phase, we tuned the hyperparameters of a single I1 run to find a good negative log likelihood on a held out validation set. The Gaussian posterior with the best negative log likelihood was then constructed several times with a varying random seed to build a mixture of Gaussian posterior. And when selecting the hyperparameters, we roughly tried to keep the overall computational budget of the entire mixture within 10 times of the standard training. And luckily, I didn't have to do that much parameter tuning because in Japan, there's a great compute infrastructure available with the Raiden and Tsubame supercomputers and the amazing weights and biases website. So we could just run things overnight and wake up the next morning to see the good runs. So for this public evaluation phase, we got first place on Cypher 10 with a method which used one MC sample, 120 epochs, 6 Gaussians, also on UCI gap. And on MetMnist, we could only get first place with a very expensive setup using 5 MC samples, 300 epochs, and 16 ensemble members. And this was too expensive. And with a cheaper solution, we did not manage to get to the first place. We only arrived at the fourth place. Similarly, for the final phase, we submitted the cheap versions, which got us the first place on UCI gap and Cypher 10, while on MNIST, we arrived at the third place with this method. So to summarize our method, going back to the beginning, how do we construct a good approximate posterior? We try to follow the principles A, B, and C to have a structured approximation, to explore locally around the minimum, but also to look at multiple minima. And the Bayesian learning rule provides a flexible framework to have different approaches both for A, B, and C. So what did we actually do in this challenge? For A, we looked at the diagonal Hessian approximation. For B, to explore around the minimum, we used variational inference. And for C, we found the diverse minima simply by changing the random seed. And of course, this can be, all of these points can be greatly improved. And for A, one can consider non-diagonal covariance approximations, which have been recently proposed by members of our group. And for C, there are smarter ways to explore the diverse minima than simply changing the random seed. So first of all, one could optimize the weights in the mixture, in the Gaussian mixture model, which we did not do. So we set uniform weights, and we can do a joint optimization of the mixture using a joint entropy term, which makes the individual Gaussian components repulsive. And this has been already proposed in theory, but so far we did not implement it. And we hope this will further improve the results. Okay, so if you want to learn more about these type of methods, there's a great tutorial by MTS Khan at NeurIPS 2019, which gives an amazing introduction to these type of methods. And yeah, thank you for your attention.
Yeah, thank you so much for the talk. So we have some time for questions right now. So if anyone in the audience has questions, so feel free to ask. And maybe I'll ask you in the meantime. So like you mentioned that ensembling generally improves the results. So do you know how, like basically how the results that you get depend on the number of Gaussians? So yeah.
Yes, so we did some evaluation on this, and the more Gaussians we put, we generally kept increasing. But we wanted to stay within the computational budget, so we did not go crazy with the Gaussians. But there was definitely a monotone trend.
And was it saturating, or would you say that like then taking from 6 to like 16 would give you a big improvement still?
6 to 16 gave an improvement, but it then around 16 it was saturating. And I suspect that some kind of repulsive term might help. So because we did not do any efforts to make these ensemble members diverse, we kept the same hyperparameters. We did not play with the initialization. We just changed the random seed, nothing else. So maybe that's why the saturation effect also happened.
So I see we have 2 questions in the chat. So I guess Seb Farquhar, do you want to unmute and just ask your question?
Sure. Can you hear me?
Yep.
So great talk. I love the entry and love your presentation on it. I was sort of, when we were thinking about the competition, I wasn't sure how the computational constraints were going to play out. So I really enjoyed seeing how you tested a few different levels and then ended up adapting your approach, and it really influenced the scores because of the computational constraints. Was that something you sort of addressed right at the end when you were tuning your hyperparameters? Did it enter the decision-making as you explored the different methods or your approach? And how would you, if it did sort of come on later at the end, how do you think it might have influenced the research process earlier on to design around those constraints throughout?
So to be honest, we only found out at the end. We were maybe a bit lazy to read the rules. So we found only at the end out about this budget. And then we were scrambling we had good results with 16 Gaussians and a lot of MC samples. And then we spent 1 week scrambling, tuning parameters to get the same results with a cheaper budget. And actually we improved because we just kept tuning, but on some data sets. But yeah, it was more that we found out at the end. So but luckily the method we used was not too computationally heavy because it has about the same complexity as standard training if you use one MC sample.
Great. Yeah, and so we have more questions. So Tim D. Hunt, do you want to unmute and ask? Okay, I'll just read the question. So the question is, he says, thank you for the talk, love the work around the Bayesian learning rule. Can you elaborate on why MedMnist was was more difficult for your method to achieve the top performance or to best the competition?
We don't know, and we would like to find out. So we were really trying to find it out, and yeah, we don't know. It's a simple answer.
Interestingly, the best method on the MedMnist was actually deep ensembles. So the team submitted a method that wasn't really constructing any Gaussians or like making any distributions. It was just using deep ensembles, and they achieved the best results. So that was quite interesting. Unfortunately, they will not be able to present today, but yeah, they sent us a description. Ingjen, do you want?
One remark: when we used 16 Gaussians, we had very good results on MedMnist. So probably going with a lot of ensemble members and not so much other things is maybe good here.
Yep. Ingjen, did you want to ask your question?
Sure. Can you hear me?
Yes.
Okay, great. So thanks, Thomas, for your great presentation and your great work. And I'd like to pick out the point on the diversity of the ensembles, right? So first, I was wondering whether you have looked at specifically how diverse the members of your ensemble. For example, do you see, say, overlapping members in your ensemble, or they are generally very different? And second, have you compare, for example, like this Vong or iVong approach to, let's say, doing ensemble training with HED, and do you find they find very different say members in ensemble?
Yeah, very good question. So we did not look at the diversity, but we compared with standard SGD, and we found that the iVong gave better results using fewer members in the ensemble than the standard SGD with more members. So this is here listed under multiple minima, where the iVong could beat 20 plus nets with 8 Gaussians or so. We did not look at the diversity. Yeah, this I cannot say anything about that, unfortunately, because also diversity should probably be evaluated in function space, maybe, and yeah, we did not do it.
Great. So and then Flavio, do you want to ask your question?
Sure. First of all, thank you for the great talk. I really enjoyed it, and also congratulations on winning the competition. My question is actually very simple. I was just wondering, like, you use mostly this ResNet architecture, but of course it's not the only type of architecture or the only type of data. And I mean, I guess you didn't test it on other architectures and stuff like that, but I would be really interested what's your feeling on how this would work on other architectures and also on other types of data. For example, thinking about, you know, transformers, graph neural networks, and things like that.
Okay, yeah, very, very good point. I cannot say anything about transformers. I have a hunch that it will work well for transformers, but this is due to the fact that some methods are based on like the sharpness aware minimization, like the SAM methods. They've been to give a huge boost on transformers, and this is also some type of weight perturbation method. So we haven't run it yet, but I'm thinking that these iVong type methods could show their true potential when running it on transformers, but it's just, I guess, it might not work in the end. And for the final phase, there was not only the ResNet. So the UCI gap was a fully connected network, a small one, and MedMnist was a LUNet 5, I think. And so there's some small diversity in the architectures, but of course it's a very interesting direction for future research to see how well these methods work on, let's say, graph neural nets or transformers. And we did not look into it yet.
Great. Yeah, and so for the last question, I'll rephrase it a bit. So I'll ask you, so how much do you think tuning the hyperparameters was important for achieving good results, how sensitive the results are to good hyperparameters, and how like do the hyperparameters generalize between different datasets, for example?
It's a very good question, and we used quite different parameters between the three datasets, and we did not try to find a unifying set of hyperparameters which works for any dataset, and also we did not set the prior variance to the one should have been. So it was all tuned based, but it was tuned based on the negative log likelihood, which is quite different than the TV distance to the posterior and so on.
Yeah,
but they were very different, the hyperparameters for the models.
Yeah. Okay. So thank you for the presentation. Yeah, it's fascinating. It's actually quite interesting that you were doing parameters based on the kind of performance, because on one of our test sets, which is on CIFAR, we used corrupted images as test examples, and on those, the performance of the HMC is actually very, very bad. So it's interesting that you still achieved the best results. So yeah, thank you so much for the presentation, and we'll now proceed to the next one.
Thank you.
So Nikita and Achille, do you want to?
Yes, sure. Let me share my screen. Can you see it?
Yes.
Okay, awesome. First of all, on behalf of our team, I would like to thank organizers for such a beautiful and exciting event. It was really a pleasure to take part in it. My congratulations to Thomas, and thank you for the awesome presentation. My name is Nikita Kotelevskii. I am a PhD student of Skolkovo Institute of Science and Technology. And today with Achille, who is a PhD student of École Polytechnique, we will present our solution for the competition. We took second place on both tracks. Yeah, and we will tell you how we managed to do it. But before we start, I want to also on behalf of our team to express special thanks to people who helped us, to Yazid Genati, Eric Moulin, Maxime Panov, Maxime Vano, and yeah, I think that we could start. Yeah.
Maybe I can just start introducing quickly the ideas around our presentation. I think we all went through with the similar solutions in the end. Basically, the point was to approximate HMC samples. So HMC is a non-local MCMC method, which is compared to other MCMC methods, which we can. So we are part of an MCMC team with Eric Moulin and other guys like this. So we're kind of through on this MCMC things. And so compared to Langevin MCMC or SGLD and stuff like this, which are the only method we can use actually with a lower computational budget, it's hard to have multimodal typically solutions. So the idea was to use the swag and the multi-swag approach, especially so ensembling different points to have this kind of multimodal solution, as Thomas presented very nicely in his first presentation. So the idea was to run different optimization chains and then try to explore with the local MCMC method, SGLD, the mode, and to try to derive some proposal distribution using the swag framework developed again by Arnaud and Pavel. And the idea is that this method, ensembling loads of these different methods, might effectively approximate the HMC, the non-local HMC samples and their predictive distribution. So to present quickly the SWAG framework, and I know Pavel will interrupt me if I say something wrong at some point. So the idea is to feed some neural, just the general idea is to feed some neural network to the data, and at the end of the training procedure, start collecting some weight samples, and on those collected weight samples at the end of the procedure, so when the points seem to have reached some kind of local minima, build a Gaussian distribution. So Gaussian distribution, which is defined then by its mean and its variance, to approximate what's going to happen in the mode of this the posterior we're trying to approximate. To collect the mean and the variance. So the mean is quite easy to collect, but the covariance is more difficult, and we'll present that in a moment. But just to summarize what is our course algorithm. So in the end, what we're going to do is run a few chains of optimization with the EDAM optimizer. A crucial thing in our experiments was that using the cyclical learning rate was really helpful. In particular, the intuition behind it might be that the cyclical learning rate allowed us to get inside some large valleys of the posterior, some larger regions, and not very thin local minima. And then at the end of this few optimization chains, run a few SGLD chain from the warm start. So in those in the modes of the posterior distribution, collecting the samples from each of the SGLD chain allowed us to compute the mean and the approximate covariance. And I'll go through the covariance on the next slides. From this proposal Gaussian distribution. In the end, we could use this Gaussian distribution as an approximate, not as the approximate posterior. And ensembling loads of this Gaussian distribution, exactly as Thomas did, allowed us to do a mixture of Gaussian distribution in the end to approximate well the posterior and the HMC samples. And we put a bit of effort to compute the subspace, and how to compute the covariance. So the idea was to use some diagonal plus low rank approximation for the covariance. So the diagonal is quite easy in our case to estimate, because we just want to compute the empirical variance of the weight according to each of the dimensions. So that's really the diagonal of the covariance which we compute there. But we want to add a bit more information, which we found was really helpful to have an informative Gaussian distribution. And for this, using the weights that we have that we collected, and again, this is I need to give Pavel and Arnaud the credit for this idea and for this PCA space. The idea was to run the PCA on the or some SVD on the collected weights that we have used that we have collected using the SGLD on the modes, and and this would allow us to compute some low rank approximation of the covariance matrix. In the end, this gives us a good way of computing the approximate covariance of the weights around the mode of the posterior. We were discussing and trying to enhance this method as well. One idea was also to consider the fact that there are loads of symmetries in this neural network. We are still struggling to understand all of the different intuitions to have in the Bayesian deep learning. But what felt interesting for us is that the different layers seem to behave kind of independently sometimes. And so what was interesting is to try to factorize by hand, like to force the factorization of the covariance depending on the layers. So in the end, we had 3 different possibilities on the same as SGLD chains. We had 3 different possibilities for estimating this covariance matrix. Either we could collect all of the weights at once, and so compute some covariance over the whole space states. So for SciFi, it was around 300,000 parameters, for example, or for the ResNet 20. I don't have the figure for the AlexNet, but typically a few 100,000 parameters. But we could also try to compute this covariance and to do this layer by layer. Doing this allowed us to force the factorization and to have a block covariance layer by layer, and it allowed us to enhance this computation there. another idea we had, and we tried to split even further. So for big layers, typically for the fully connected layers, which were at the end of the networks, we had again a few dozens of thousands of parameters, and we also tried to split this layer into batches, which helped as well the computation of the covariance. And overall, this whole method allowed us to compute the mean, which was just the average of our Achille chain, and different types of covariance to compute all of our Gaussian proposal distribution. And ensembling all of them gave the final approximate posterior we were using.
Okay, let me switch to the training procedure and to tricks we used during the competition. For this moment, we have already talked everything about the theory, and now we will be mostly concentrated on engineering approach. During the development phase, we noticed that it's crucial to split the whole optimization procedure into two phases. The first phase will be, the aim of the first phase will be to reach the maximum a posteriori estimate of weights. And for this problem, we typically used Adam optimizer with cyclical learning rate. We noticed that it helps a lot. Well, it's known in deep learning that cyclical learning rates allows us to achieve a better local minimum, and apparently it works here as well. And when this first optimization phase is finished, we typically run like one optimization chain or at most two, because it's quite expensive. We run the second sort of optimization phase. Why sort of optimization phase? Because we don't really aim here to reach the local optimum, but rather we want to explore. And for that, we are using SGLD with RMS prop preconditioner. I think that something similar was told by Thomas before. And at this phase, we also decrease learning rate because we don't want our current chains to move far from the local mode we reached during the first phase. And typically, these both phases, they have similar computational complexity. Okay. Apparently, we have loads of hyperparameters for our method. Despite, well, we can artificially split them into two groups. The first group is sort of classical for all deep learning models, like the strength of L2 regularization or the temperature of likelihood. But also we have here specific hyperparameters like type of subspaces we use, and if we split them into batches, the size of these batches. So the tuning of these hyperparameters is a vital problem. And we need a held-out data set to tune them. But we given only training data and labels, but not the predictive distribution on the test data sets. And what do we want to have is to at least some proxy to the data set, to the HMC predictive distribution from the leaderboard. And thus, we need a way to sort of de-anonymize given holdout data sets to be able to tune hyperparameters. Yeah, this is the example of the config file we had. So you see here, it's just for the sake of illustration. You see that here we have a huge amount of hyperparameters, and it's very vital to tune them. To summarize, we are given anonymized test data for, I call it challenge data sets, but by this I mean the data sets on the leaderboard. And we have HMC samples and HMC predictive distribution for development phase. And what do we want to have is at least labeled data for leaderboard data sets and possibly fair HMC predictive distribution for them. We have 3 data sets. they have different complexity, both architecture-wise and data-wise. So let us start from the very simple data set. It's UCI energy. It's a regression data set, and to receive a predictive distribution, we are using here just a multi-layer perceptron consisting of two linear layers, if I'm not mistaken. And the architecture and the data set itself is amenable for running a full batch HMC, even on the laptop we have. So to receive a proxy and for tuning these hyperparameters, we simply ran the HMC for this data. For MedMinist, it is more complicated because the data set is big and it's impossible given our resources to run the full batch HMC, but it's available online. And we de-anonymized labels for test split, and that's actually what all we can do. We just simply casted these labels into degenerate distribution of the labels, and thus we can achieve the proxy to the, not even proxy, but the accuracy of HMT samples from the leaderboard. And during the hyperparameter tuning, we can use this accuracy as a metric. And for Cypher 10, despite it's the most complex data set, we were given samples, HMC predictive distribution samples on development phase. So no magic here for Cypher 10, we can just use them. As was asked before and mentioned by Thomas, for each of these data sets, we have different set of hyperparameters, but probably it is expected because we know that there is no free lunch, and we have to tune, even for globally the same concept, we have to tune hyperparameters separately for all of them. I think it finalizes our presentation. Yeah, this the references to the papers we used. Yeah, we are lucky to see the authors of first two papers here in this chat, in this conference. Yeah, thank you for your presentation. And if you have any questions, we are happy to answer them.
Yeah, thank you for the presentation. So, Ingjen, do you want to ask the question?
Sure. I think I'm just interested in exactly how you initialize your HGRD parallel chains, right? So you said that you only run one atom or one or two atom chains for initialization, right? So then did you initialize your HGRD parallel chains from the same local minimum found by the atom chain?
Yeah, so we split into two. If we run two Adam chains first, and we have two warm starts, we split into two GSGLD chains and half of them start at the first point provided by the optimization, and and the other half by the other one point. A crucial thing is that we start SGLD with quite a high learning rate or quite a high step size, and then decrease the step size so that the SGLD chain have some time to diffuse and all explore basically our intuitions that they all can explore a different part of the mode they're into.
Okay, yeah. So you're saying that even when you initialize from one chain, you'll still be able to escape somehow from that local optimum and then go to some nearby thing, or this is not the case?
I don't know if we escape. I wouldn't be able to tell if we really escape from the mode. But we do have some diversity in the results even provided by each of the SGLD chain. That's what we had observed.
Okay, thanks.
When we have this decreasing basically step size for SGLD, we start with the step size decreased by a factor 100 over the whole chain, basically, typically.
Okay, thank you.
Thank you. And I wanted to ask about the SGLD. So you mentioned that temperature was one of the parameters that you considered tunable. So did you find that, like, what temperature did you use in the end?
I think we
Typically-
use the temperature of 1 almost in most of the data sets.
Did you say 1 or?
Yeah, a temperature of 1. We didn't find it. We had trouble. Or correct me if I'm wrong, Nikita. But for the
Well, typically, yes, indeed, we use a temperature of order of 1. But you know, when I tried to change it a little bit, the results did not change a lot. So
yeah.
We just use the values. Yes, if I'm not mistaken, the final version consists only of temperature of 1, but we also tried the vicinity of 1 as well, and the results were like
similar.
Cool. And yeah, so you mentioned that you considered 3 different strategies for splitting the covariance matrix. So did you have like results for how they compare to each other? Which one do you then?
At this moment, we don't have a slide to show them, but typically what we found is that for carefully chosen, well, we did not mention one very important hyperparameter here, which is the sort of scale of this covariance. So once we have built a covariance matrix, we also can sort of scale it, scale the amount of noise from it. And if the hyperparameter is chosen carefully, the more subspaces we have, the better result is. But you should keep in mind that this layer by layer subspaces, they're quite expensive to build and to sample from them, because well, as a author of SWAG, you remember that ultimately you have to perform several samplings, and if you sample independently from each layer, you have to do a lot of operations. So yeah.
Thank you. So if we don't have any more questions, I guess let's move on to our final speaker, Arnaud.
Thanks a lot.
Thank you.
Thank you.
Yes, let me share my screen. Okay, do you see my slides?
Yes.
Okay, so hi everyone. So first I want to take the opportunity to thank the organizers of the Bayesian deep learning competition for this competition, but also for the benchmarks, which I'm sure will be very useful to Bayesian deep learning community. So let me introduce our team. So my name is Arnaud Delaunoy, and I'm a PhD student at the University of Liège in Belgium. And there I'm advised by Professor Gilles Loup, and I have interest in simulation-based inference and uncertainty quantification. So we present our solution, which is based on an algorithm that we call sequential anchored ensembles, which is an extension of an algorithm called anchored ensembles from Tim Pierce and collaborators. So let me first introduce the notation. So we denote by D the data sets, by theta the neural network parameters, by X the inputs, and by Y the outputs. And we want to compute the predictive distribution of the outputs given the inputs and the data set. And for that, we need to approximate the posterior of the neural network parameters given the data set. So we base our work on anchored ensembles from Tim Pierce and collaborators. And these works aim at training an ensemble of neural networks such that the members of the ensembles approximately follow the Bayesian posterior. And for that, they modify the training procedure. And on prediction, you simply average the predictions of the members of the ensemble. So the idea is to inject noise in the training procedure for the optima to be sampled from the Bayesian posterior. So here you have the algorithm. So they first sample what they call anchors, and then they initialize the neural networks, and they train on a modified objective which replaces the prior by something we call p-anch. which is basically a normal distribution centered around this anchor. And so there are several hypotheses to this method. First, it only works with a normal prior, which is the case for all the benchmarks in these competitions. And it also assumes a normal likelihood, which is only the case for the UCE gap dataset. But although the mathematical derivations are based on this hypothesis, it also works in practice for classification. And so they show that if those anchors are sampled from the prior, then the obtained optima are approximately sampled from the Bayesian posterior. And so a drawback to this is that training an ensemble is computationally expensive. So here you see that in 200 epochs, we only get 2 samples from the Bayesian posterior, because for each sample, we have to make a full training procedure. So the idea behind our algorithm is that if 2 anchors are close to each other, so should be 2 optimum. And so we, instead of building all the ensembles from scratch, we start from the previously obtained solution. And so the algorithm works as follows. We first sample an anchor from the prior, and then we make a first long training of 100 epochs. And then we draw another anchor and we train starting from the previous obtained solution. And hopefully this training is much shorter and will allow to build larger ensembles. And so we need to have anchors that are close to each other, but eventually span the whole prior distribution. And so for this, we draw the anchor for an MCMC procedure that actually run on the prior. And then we actually exploit the fact that the MCMC procedure will produce correlated samples that are close to each other. And so we have short trainings to allow to build large ensembles, but of course it comes at the price of having correlated ensemble members. But we can run this procedure several times to benefit from different initializations and then have kind of mix of both worlds. So here is how the algorithm behaves. So we can see with anchored ensemble, we start from a very high loss, while with sequential anchored ensemble, we start from the previous obtained solution, and we still have a small peak because we modify slightly the objective function, but we are able to converge much faster. And so in this plot, we are able to construct an ensemble of 21 members in the same time anchored ensembles construct an ensemble of 2 members. So for the algorithm to work well, we need that 2 anchors are close to each other, but well, 2 consecutive anchors are close to each other, but that eventually it spans the prior well. And so for that, we run a guided walk metropolis hasting procedure. And so it works like a classical metropolis hasting procedure. So you make some transitions that are either accepted or rejected. But the difference lies in the fact that the transitions are always performed in the same direction until rejection. So you will always move in the same direction until rejection, and then you will invert the direction until the next rejection, and so forth. And so you can see here the black dot always move in the same direction until a rejection. And what's interesting here is that we know that we will run this MC procedure on Gaussian, and so a rejection cannot occur until the peak is passed. So the black dot will just move to the peak until it's passed, and then at some point we'll have a rejection and move in the other direction. So this is for 1 parameters, and of course neural networks have more than 1 parameter, but under the prior we know that those parameters are independent, so we run 1 chain per parameter. And this allows us also to always have some parameters that move and not have all the parameters frozen on a rejection. So here is the algorithm. You sample a transition from a normal distribution, and we denote the transition by Z. And then you take the absolute value of this transition and multiply it by a variable called D for the direction, which can either be positive or negative. And then you compute the acceptance rate, and on acceptance, you keep the same direction, and on rejection, you invert the direction. So one question remains is how to choose this transition standard deviation. First, it should be as small as possible because you want to make small transitions so that you have fast training, but it should span the prior at the end. And the thing is, as this MCMT procedure run on the prior, which is known, we can verify if it spans the prior, and so we can make such kind of plots. And here we see that, for example, for the standard deviation of 0.01, each chain is stuck between -1 and 1.5, and so the standard deviation is too low, and here I would choose a standard deviation of 0.03 or 0.05. So just to give an order of magnitude, so in this competition, we have a computational budget of 1,000 epochs. So if we make trainings of 100 epochs with anchored ensembles, we get an ensemble of 10 members. While with sequential anchored ensembles, we were able to construct an ensemble of 351 members. And so what we do is we run the procedure 3 times, and each time we first make a long training of 100 epochs, and then we make short sequential trainings of 2 epochs. We also evaluate our method on 10,000 epochs, where we are able to construct an ensemble of 4,510 members. But of course, those are correlated. So here are the results, and we can see that on the CIFAR dataset with both architecture, we're able to have better results than anchored ensembles with sequential anchored ensembles. On IMDb and MNIST, we are kind of even and we perform a bit worse on UCE gap datasets. For now, the reason for this are still a bit unclear, but we can postulate that some posteriors are easier to navigate than others, and so some posteriors benefit more from different initializations, but mostly we don't know at this point, and we should explore this. Just something interesting to note is that usually we perform better in total variation than in agreement. So it can be seen on the MNIST dataset where we perform better in total variation, but worse in agreement. It can also be seen here where we have a better total variation, but a worse agreement than anchored ensemble trained on 10,000 epochs. And that's something also we see on the leaderboard where we are always better ranked in total variation than agreement. So even if our method is not able to make the same prediction, we seem to still better match the posterior. So that's all for me. So thank you for listening. And if you have questions, feel free to ask it in the chat or to contact me by mail or via Twitter.
Okay, thank you so much. So we have a question from Ingrid. Ingrid, do you want to ask?
Yes, okay, so the presentation actually answers part of my question, but also raised another more interesting question. So basically I have, maybe let me rephrase the question again. So you do this kind of, say, sequential initialization to get the prior samples, right? But you don't actually get some samples from prior. Instead, you do this kind of, say, the multiplicity hastings to get samples. So my first question is essentially, it seems to me that your rest of the members in your ensemble are, say, initialized near the last answer and then trained in a shorter time. So would you still expect that your ensemble to be diverse? So that's the first question. And the second question is about the way you choose to say, okay, I want to evaluate whether my samples are actually covering the prior, and you show some sort of, say, independent dimension plot to show that it is the case. But in high dimensions, if you actually cover the prior, then each of the prior samples, they will actually be very far away from each other, right? That's because you have very high dimensions. Then how would you actually expect that only training for like 2 or 3 epochs will actually give you some good answer for each of the ensemble?
Okay, so first for the diversity, basically if the MCMT procedure span the prior, we should span the objective functions defined here, but of course you have this likelihood term, which may be difficult to navigate, but we didn't make much test to see if our ensemble was diverse or not. But of course, we expect it to be at some point stuck in a local minima, and that's why we run this procedure multiple times to capture multiple local minima. And yeah, regarding your second question, that we're actually looking at the join, here we are looking at the marginal, and what we're interested in is the join. Yes, you are right. It's kind of not sufficient for a test, but I think it gives a good intuition. But yeah, maybe we should do some statistical tests to see if we cover the prior in multiple dimensions.
Yeah, I think essentially my intuition is that if your samples are really covering the prior, even in the joint space, right, then your initial interactions of the ensembles will be very far away from each other. Then I won't actually expect that, say, you only need to train for a few more epochs to actually get a good solution. So yeah, that's something that's puzzling me on why this approach works.
Yeah. I'm not sure to have understood everything, sorry, but...
Okay, so yeah, I also had a question. So you mentioned that you do kind of several runs of this procedure. So so I guess there is a trade-off, right, between like how many independent runs you want and like how many of the sequential updates of your ensemble you want to do. So what's like kind of what's your way of deciding on how to split the compute?
Yeah, basically I tested several hyperparameters and I evaluated on the negative log likelihood. So I splitted my dataset in a training and a validation dataset. And then I just tried one chain, two chain, until several chains. And for a budget of 1000 epochs, I found that usually 3 chains work well, while we would have 10 members if we were training all independently.
I see. Yep. Thank you. And I see another question in the chat from Sandeep. Did you want to unmute and ask?
Sure. First of all, thanks for a great talk. So I was curious, when you're doing the sequential learning, right? Do you generally see the accuracy or the loss similar on these ensembles, or do you see a trend of increasing or decreasing accuracy?
Well, it depends on the benchmarks. On Cypher10 with ResNet, we see that the accuracy is slightly increasing during the training, but on the other data set, we see that it's slightly decreasing, meaning that probably we are not reaching the optima with 2 epochs. But still, if we look at the performance of the ensemble in the end, when I try to train for longer than 2 epochs and have smaller ensembles, I get worse results.
I see. Thank you.
Okay. Yes, thank you so much for the presentation. And I believe this concludes our event today. So yeah, I guess from all the organizers, I wanted to say a huge thank you to all of the participants. We received a lot of really exciting submissions, and all of these methods that were presented today are actually novel. So we do see like novel research being done based on this competition, which was really exciting to me and to all of the organizers. So thank you so much for putting the effort and time in the competition, and it wouldn't be possible without you. So yeah, thank you. And the meeting is recorded and we will be posting it online very soon. Yeah. All right then. So if no one else wants, if anyone wants to say something, so feel free, but otherwise, yeah, it was great having you here, guys. Thank you.